So, last lecture we went through some calculus and derived our kinematic equations for constant acceleration. Today, what we're going to do is briefly recap everything we've done and then work through one simple example of how we can use everything we've learned to sort of quantitatively solve kinematic problems where we're trying to describe motion. So, just a quick recap. We started this class by introducing the words and the concepts we are going to use to describe motion. This was position, velocity, acceleration, and how all of those related to time. They have direction and a magnitude. So we've been working in one-dimensional problems and one-dimensional situations right now. So we would define some positive direction, and a positive position or velocity or acceleration would be something in that positive direction, whereas a negative acceleration, say, would be an acceleration that is directed towards the negative direction. We also looked at how to visualize motion. That we used what we called motion diagrams. We developed some graphical representations as well that related to calculus we went through in the last video. We started with quantitative analysis of how we could, put some numbers to velocity and acceleration and position. For position, all we needed to do was really define a coordinate system, some zero in the universe we're going to describe, or the frame of reference we're describing the situation from, and then the position was simply the distance in that coordinate system. Then we looked at the velocity, which was the change in position over a change in time, and that calculated our average velocity. As that change in time that we were looking at got smaller and smaller, if we took the limit as that went to zero, we would get the instantaneous velocity, which is just the derivative of position with respect to time. Likewise, acceleration was the change in velocity with respect to time, and taking the limit of that time interval going to zero, we got the derivative of velocity with respect to time. Going the other way, thanks to what we know from our calculus courses and that, if you wanted to know the change in position and you had the velocity as a function of time, we could simply just integrate that over the time interval to get the displacement or the change in position. And likewise, if we had the acceleration as a function of time, we could integrate that to get the change in velocity. Now, last class, we used all of those things and derived what we call the kinematic equations for constant acceleration. And there were three of them. The first one was just the velocity at some later time. Is equal to the initial velocity plus the acceleration times the delta t. Now, a quick note on notation here from the textbook is what I'm following and showing here. They use this s, which I have not used in lectures so far. It is just a general direction. If you're describing motion of something moving, say, left to right, it might be natural for you to use the variable x. If you're describing motion going up and down, you might prefer to use the variable y. In this notation, all you end up doing is substituting that x or y or whatever label you're using for your given direction for the s. So this first equation would be the subscripts mean the velocity. The final velocity in the s direction is equal to the initial velocity in the s direction plus the acceleration in the s direction times delta t. Likewise, the position equation is the final position in the x direction, or the s, in general, the s direction, is equal to the initial position in the s direction plus the initial velocity in the s direction times delta t plus 1/2 the acceleration in the s direction, delta t squared. Then if we take both those equations and eliminate time by doing some algebra with them, we end up with the third equation shown there. Today what we're going to do is we're going to take these equations, take all that we've sort of discussed in the course so far, and the fact that acceleration when something is in free fall is constant, and we're going to work through an example. So I just mentioned acceleration in free fall is constant. This is something a lot of you may have probably already heard of. If you've been keeping up with the reading, you've definitely read that so far. I'm not going to get into why this is true. We'll cover this when we get to Newton's laws in the second part of the course. But it turns out that anytime there's some object near the surface of Earth that is not being touched by anything else, right? So it's just in free fall. It's free to fall towards Earth. It is going to accelerate straight down towards Earth with a constant acceleration, and that acceleration is 9.8 meters per second squared. So if I have anything, if I drop something, if I throw something, if I do everything, as soon as it's in motion or near Earth and not being touched, it is going to start accelerating towards Earth with that acceleration of 9.8 meters per second squared. So today we're going to use that fact and everything we've learned and solve a problem. So what's a problem we could do? Let's just say I grab an object, I take a ball, I hold it up above my head, and I drop it. And I ask, how long does it take for that ball to reach the ground? So ball drop from, we'll say 8 feet if I hold my hand straight up. And the question is, how long does that ball take to hit the ground? So let's sort of go through this brute force and use everything that we've discussed in this course. Starting with, how do I visualize this motion? All right. A lot of students, I get the impression when we're first going through this stuff in this course, think that, drawing a picture is a bit pedantic and I don't have to do it. You don't. A lot of the things we're going through and covering are just tools that will help you when you get to problems like this to solve. And almost every time a student comes to me for office hours with a problem and we start working through it, the quickest way to get that student to realize a solution is to have them draw a picture. So although it may seem pedantic, it is an excellent way of organizing your thoughts and thinking and your approach to the problem. So let's look at what's happening with this ball. So I hold it up above my head there, I drop it, and it accelerates downwards towards the Earth. So my motion diagram might look something like that. All right. Now, for a good motion diagram, I'm going to want to have a coordinate system. So I'm going to just draw a coordinate system, and we'll call that the y direction, like that. And I'm free to choose any origin I want, but just for simplicity, I'm going to choose the ground as being my zero, my origin for that y direction. All right. What else? Well, I know I have velocity vectors that I can indicate with those things. They're going to be coming down like that. And if I also wanted to add acceleration vectors, we're familiar with how to do that. As those velocity vectors get larger and larger, pointed down, they're accelerating downward. So we've got, something we probably all visualized in our heads, a nice representation of what I expect with this ball dropping. Now, I can move on to the next thing we did, which is how we describe motion, right? So we use those three terms: position, velocity, acceleration, all with respect to time. So I'm going to use y variables. I've labeled my coordinate system y. So y for position, I'm going to have velocities, going to be v's, accelerations a, and t time. So this is sort of the variables I'm using, and I want a variable for each, all the important parts of the problem, right? So I want to describe, at the start, I know a lot about where my system is. I've held up the ball. So I'm going to have initial positions and velocities, and I want to know about when it hits the ground. So I'm going to want final ones. So what I'm going to do is I'm just going to label, my initial position, my initial velocity, and my initial time. And then likewise, at the end, I'm going to label my final position, my final velocity, and my final time, right? And you'll notice I haven't labeled acceleration yet because it turns out this is in free fall. There is a constant acceleration for this whole problem. So I don't want to label an initial acceleration, a final acceleration. There's just one acceleration for this entire motion I'm trying to describe. And that acceleration is that acceleration due to free fall, 9.8 meters per second squared. And it's in the negative direction, right? I've labeled this up as my positive direction, so the acceleration is pointed downwards, so it has to have that negative sign giving it its direction. What else? Do I know any other of these variables? I've just labeled, I'm going to need to know, these are the variables I'm going to use to describe this problem in my mathematical picture. Do I know any values for them? Well, my initial position, I dropped it from 8 feet, so I know that's 8 feet, right? My initial velocity, I didn't throw it, I just let it go. So when I let it go, it wasn't moving. It had 0 meters per second was its velocity. And time, I'm free to choose any origin I want. Might as well start the clock when I start the problem. So initial time is 0. What about the final values? Well, the ball hits the ground at the end here at its final time, and that position is, I've defined that as the origin of my coordinate system, so my final position is 0 meters. My final velocity, this is something that'll, can cause a lot of confusion at the start, but essentially I don't know it yet. Remember, we're trying to describe the motion as the ball falls, when it has that constant acceleration. And so we're not describing after it's hit. We're describing the motion right up till when it hits the ground, right? That's when the acceleration is going to be constant. As soon as it touches the ground, it's going to change its acceleration, and we can't describe that without more information. So the final velocity, I don't know. Don't think of this as what happens after it hits the ground. Think of it as what is the velocity it hit the ground with. So it's not 0. What about the final time? I don't know. That was actually what was asked. So now we're ready to take what we've set up, our nice visualization and our nice definition of the things we know about the problem, and apply our kinematic equations for constant acceleration. So if you recall, the first one was V final is equal to V initial plus acceleration times the delta t. The position one was Y final is equal to Y initial plus V initial delta t plus 1/2 a delta t squared. And then finally we have V final squared is equal to V initial squared plus 2a delta y. So these were our 3 kinematic equations for constant acceleration, and they are true and apply to any situation where that acceleration is constant. And we're in free fall, we know we have that constant acceleration. So these 3 equations will correctly describe the motion and connect our initial points to our final points. All we have to do now that we've set this up is connect our final to our initial properties or descriptions with these equations. So all of them are true. Not all of them are going to give you the information you want, but they're not wrong. So if you say, all right, I'm going to apply this equation, say this third one to it, and you apply it, and you don't really get any new information or anything, that's not wrong. You've just spent a little time trying something that didn't get you what you wanted. So don't panic if you've applied an equation and it didn't immediately spit out what you were looking for. But let's just go through this. I'm going to use the position equation. I have a lot of information about position. So what do we do that? Now we just take our nice picture here and use it to translate our kinematic equation into these numbers. So I have y final is equal to y initial plus v initial delta t plus 1/2 a delta t squared. Now if I write that out, my y final, just looking at my picture, is 0 meters. Y initial is 8 feet, but we're going to want this in the SI units. All our other units are in meters per second, meters per second square. That 8 feet is going to cause us problems if we try to cancel it. So we're going to need to convert that unit somehow. And if you look in your textbook or even just Google it, should be easy to find out that 1 meter is essentially 3.3 feet, which means 1 meter divided by 3.3 feet is equal to 1. So I can take any of those numbers and multiply it by 1. So my y initial is equal to 8 feet times 1, which is 1 meter over 3.3 feet. The feet cancel, and if I carry out that math, that ends up being 2.42 meters. So I've converted my initial position to that. I know it's 2.42 meters, right? My initial velocity is 0 meters per second, so I can substitute that in, times delta t, plus 1/2 my initial acceleration, or my acceleration rather, is negative 9.8 meters per second squared, times delta t squared. That 0 makes that term 0, and now I can start to just do some algebra to solve for what I need. So I can bring this term over to the other side because it's got that negative there. I get 9.8 meters per second squared divided by 2 times delta t squared is equal to 2.42 meters. And I can solve for that delta t. It's going to be equal to 2.42 meters times 2, all divided by 9.8 meters per second squared, all square rooted. And if I enter that into my calculator, I end up with 0.70 seconds. One thing you want to check here is, let's look at our units. All right, I was very careful to bring them through and write them down everywhere because it's very nice to see that meters does cancel. That second squared, because it's in the denominator, it's double in the denominator, I guess, comes up and it's under the square root, so it does give me seconds. So I do have the correct units. I'm looking for a time, and I got the unit of time. So that's sort of a check that should help you be a little more confident in your answer. You also want to check how realistic this time is. I mean, if you drop a ball from above your head, how long does it take to get the ground? And 0.7 seconds seems pretty reasonable to me. That's one of the nice things about mechanics and classical mechanics that we're studying in this course is we generally have a decent intuition for the values we expect for things. Anyway, we've solved that problem. We figured out how long it takes for a ball that I dropped from 8 feet to make it to the ground. If we wanted to, we could continue to go. We could figure out how fast it hit the ground with, what the speed was or the velocity of that ball was, and keep going from there. But for now, this is what we're doing. Sort of recapping the process, though. I think it's always a good idea to, when you're first approaching a problem, sort of visualize what that motion is going to look like. Draw some sort of motion diagram or figure that helps you organize and orient what you're expecting with the problem. Then label, the sort of variables we're going to use to describe that motion. We went with position, velocity, acceleration, and time, and we labeled them y, v, a, and t, and then got the specific ones for our initial and final points, the parts of the problem we were concerned with, and the acceleration that was constant, and connected them. Once you have those pictures, then it's a matter of applying and labels. Then it's a matter of applying your kinematic equations for constant acceleration. And after you've got your nice motion diagram with your labels, that's pretty much your Rosetta Stone that's going to translate our 3 equations into whatever we need and help us get to our problem.